So let me mention the asymptotic quantities that I'll be looking at. So there are two quantities. Seshadri constants and what is more or less a dual notion, Waldschmidt constants. So to motivate that, let me start by looking at a famous conjecture in which both of these things come up. So let X be a blow-up of P2 at S generic points. So there are, when S is greater than or equal to 9, there are infinitely many curves of negative self-intersection. Infinitely many curves, I'll call them E, with E squared less than 0. And in fact, from the last talk, I mentioned the SHGH conjecture, which says that if C is reduced and irreducible, that implies that C squared is greater than or equal to the arithmetic genus minus 1. So that's a conjecture. But if it's true, this says, as I mentioned before, that C squared negative implies C squared equals negative 1, and C is a smooth rational curve. So these are the curves that we know about. The negative curves of self-intersection are the exceptional curves. The smooth rational curves of self-intersection negative 1. Let me mention a few of the examples. It's easier to do it in P2. So we have the basis, the classes of the line and the blow-ups give a basis for the divisor class group on X. And so using, which I defined in the first lecture, using that, if I have 2 points, the proper transform of the line through the 2 points is an example of an exceptional curve. Self-intersection, negative 1, and it's rational. A conic through 5 points, if the points are generic, there's always an irreducible conic through the 5 points. So this is 2L minus E1 minus E5. And then if you have at least 7 points, there's the cubic with a singular point, and then through 6 additional points. So that has self-intersection negative 1. And then the other one I want to mention, there are infinitely many if I have S at least equal to 9. But I'll mention one more, and that's, it looks like this. So this has degree 6. 1, 2, 3, 4, 5. If you draw a line, it intersects it in 6 places. It took me days to figure out what this looked like. Most of the singular points are nodes, but there's a triple point. So this is 6 times the class of a line minus 1 triple point, and then 7 additional, let's see, 5, 6, 7 additional double points. That has self-intersection -1. That's another example of one of these exceptional curves. This is quite hard conjecture, and so Nagata has a related conjecture which is also quite hard, but it's not quite as hard. So let me mention Nagata's conjecture. So this conjecture doesn't depend on S being greater than or equal to 9. This is for any set of, blow up any set of generic points. But Nagata's conjecture is for S greater than or equal to 9 generic points, if those are the points you blow up, then for any irreducible reduced curve C on X, where C is linearly equivalent to D times the class of a line minus M1 E1 minus MS ES. So that's the divisor class of the divisor. The conjecture is that D is greater than or equal to the sum of the multiplicities divided by the square root of the number of points. The nice thing about this is that it's a linear expression, and this is a quadratic expression. So this should be easier to say something about. But it turns out let me call this conjecture 1. This is the SHGH conjecture. So this is a corollary of the conjecture. I'll call it conjecture 1. Conjecture 1 implies the Nagata conjecture. So if you can prove the SHGH conjecture, you've proved the Nagata conjecture. If you can disprove the Nagata conjecture, you've disproved the SHGH conjecture. And it's your choice which you want to do. I think most people think that they're both true. Let me show you what the proof is. So for the proof, I want to remind you of an easy inequality. So the inequality is these numbers are non-negative. We're just adding up a bunch of non-negative numbers and dividing by the square root of the numbers. But if you take the average of a bunch of numbers squared, that's less than or equal to the average of the squares. So statisticians use this all the time. So what that says here is if I add up the numbers and divide by S and take the square, that's less than or equal to the sum of the squares divided by S. So I want to use that fact. I'll leave this as an exercise. No, I'll get to the square root in a second. No square root. Here I'm just taking the average squared versus the average of the squares.
But that means the denominator.
Yeah, so I'm averaging. So this is I equals 1 to S. So I'm just averaging at this point. Well, we can do a quick example. Suppose the numbers are 1, 2, and 3, for example. So the average divided by 3 is 2, and I want to square it. And here I'm going to take 1 plus 4 plus 9 and average it. So this is going to be 14. And so that is 4.6. So anyway, let's assume that. So I want to prove that conjecture 1 implies the Nagata conjecture. So let's first notice that the Nagata conjecture is a linear expression. And so it's enough to prove it for reduced irreducible divisors, because if it's true for each component of a curve, it'll be true for the entire curve. So it's enough to prove, it's enough to assume C is reduced and irreducible. So let's assume that C then is linearly equivalent to D times L minus the sum of the multiplicities times the blowups. So there are two cases. Maybe the curve has non-negative self-intersection. So if that's true, that implies that d squared is greater than or equal to the sum of the multiplicities squared. And the sum of the multiplicities squared well, I can take the average of the squares and then multiply by the number of points. And that's just the same thing as the sum of the squares. But this now, if I use this inequality, this is greater than or equal to the sum of the m's divided by s squared times s. Just using this statistics fact. And then this thing simplifies to, I can take the square root inside, and this is equal to, it's equal to the sum of the squares divided by the square root. And so now, if I just take the squares away, I have the Nagata conjecture. So that's the case that c squared is greater than or equal to 0. What happens if c squared is less than 0? So here's where I want to, if c squared is less than 0, I want, at this point I'm not using the SHGH conjecture, but now I want to use it. So SHGH tells us that c squared equals -1 and c is smooth and rational. And so now by the genus formula, or adjunction if you like, c squared plus ck equals 2g minus 2. The g is equal to 0 because it's a smooth rational curve. C squared is -1. So this tells me that c dot minus k is -1. Or sorry, plus 1. I put in a minus. So minus c dot k is plus 1. But minus c dot k is 3 times the degree, and 3 times the degree minus the sum of the multiplicities. So this is, we're assuming that the number of points is at least 9. So the square root of S is at least 3. So the square root of S times D is at least 3 times D. And 3 times D is equal to the sum of the multiplicities plus 1. So 3 times D is actually greater than the sum of the multiplicities. So now we get the sum of the multiplicities divided by the square root of S is less than or equal to D. So this is motivation for talking about Seshadri constants and Waldschmidt constants, because what I want to do is I want to reformulate Nagata's conjecture in terms of Seshadri constants and Waldschmidt constants. So let's reformulate the Nagata conjecture in terms of Seshadri constants and Waldschmidt constants. One thing that's fun talking about Seshadri constants is 2 months ago I gave a lecture in Chennai, and it was about Seshadri constants, and Seshadri was there. So I don't know how much longer he'll be with us. He's getting old and he's not that healthy, but it was fun to meet him and to talk about Seshadri constants to Seshadri. I mean, what could be better? So I want to define what these things are. So to do that, let's go back to P2. Just like before, I wanted to express things in terms of points and curves on P2. And I'll do the same thing here. So we'll take a detour for a moment to talk about fat points. So fat points are subschemes of projective space. That's typically where people look at them. There's no reason to just look at P2, so I'll talk about Pn. Let's take some points in Pn. And these are distinct points. You can actually talk about infinitely near points if you like, but I'm going to assume that they're just distinct points. And what I want to do is define a subscheme, which I'll call Z, for simplicity, I'll assume that the coefficients of the points are positive. So the subscheme I mean is the following. Z is the subscheme defined by the following ideal. It's a zero-dimensional subscheme. So the ideal of Z is going to be the intersection of the ideals of the individual points raised to the power m sub I. And this is all taking place inside, K is the ground field, whatever ground field you like. Look at the coordinate ring of projective space. So that's just the polynomial ring in n plus 1 variables. So here I have a homogeneous ideal. This ideal defines a subscheme, and this Z is the subscheme that it defines. It looks like Z defines the ideal, but in actual fact, it's the ideal that's defining the subscheme. And this is the notation to define this ideal, I need to specify the points and I need to specify the multiplicities. So this notation just indicates which ideal I'm talking about. Now the thing about this is, if you blow up the points, then you can talk about a divisor. L is now the pullback of a linear space of codimension 1. So it's not a line in general, it'll be a hyperplane. L for linear. And the E's are the blow-ups of points, so they become codimension 1. Well, they're isomorphic to Pn minus 1. So it's one dimension less. But this works just like it does in P2. I get a divisor, and it turns out that on the blow-up, the dimension, the group of global sections is canonically isomorphic to the ideal in dimension D. So this is a homogeneous ideal. So that means it's a direct sum of the spans of the homogeneous forms of degree D in the ideal. And so this is just the vector space span of the forms of degree D in the ideal. And it's canonically isomorphic to this group of global sections. So actually, any question that you're interested in that you can express in terms of global sections of line bundles on this P, on the blow-up, you can also discuss in terms of homogeneous ideals downstairs. So it's equivalent. You can look at it either way. And I want to define the Seshadri constant in terms of the commutative algebra rather than the geometry, just for simplicity. You don't have to do this. So the Seshadri constant I'll define the Seshadri constant of Z. So the Seshadri constant is defined the following way. Oh, so for the Seshadri constant, I want to go back to P2. You don't have to, but I don't want to go into complications. So I'm back on P2 now, where I have intersection theory. So E sub Z is the supremum of all T. Well, I'll write down what I want, such that L minus T of M1, E1 plus etc. I want to take the largest possible value of T such that this is a Neff divisor. This divisor is in the divisor class group over the reals. But I can still talk about Neffness. So Neffness means a divisor is Neff if D dot C is non-negative for all effective divisors C. And so this is a condition imposed by infinitely many divisors. It has to be non-negative with respect to all of them. You can see what I'm doing is I'm subtracting off. This is a negative thing. The bigger T is, the less likely this is to be Neff. If T is too big, it will fail to be Neff. And so what I want is I want T to be as big as possible, just the limiting point where I still have Neffness. So that is the Seshadri constant. Let me talk about the Waldschmidt constant now, which is the Seshadri constant is in terms of neftness. The Waldschmidt constant is in terms of effectivity. So they're dual notions. So the Waldschmidt constant I'll define the following way. Let me define something called alpha. I have alpha of the ideal of a fat point scheme. Sometimes for simplicity, I'll just write alpha of the scheme itself, but it's really alpha of the ideal. And this is the least t such that the homogeneous ideal in degree t is non-zero. So what is the least degree of an element in the ideal? That's alpha. Alpha basically is the first letter of the Greek alphabet. So this is asking, what is the first place in the ideal where I get something that's not zero? The beginning of the ideal. Now the Waldschmidt constant is an asymptotic version of alpha. So I'll write it this way, alpha hat of z. What it is it's the infimum over all m greater than or equal to 1 of alpha of mz divided by m. So this is why it's asymptotic. It's kind of the limiting value of the alphas, where I take larger and larger multiples of z and divide by m. It actually is a limit. This isn't completely obvious, but it turns out that the infimum is actually the limit as m goes to infinity of alpha of mz divided by m. And so these are related in the following way. Oh, I should mention, before I mention the relationship, the Waldschmidt constant was invented by Waldschmidt. So this was 1978. He was interested in studying problems in number theory. What he was interested in is when is a complex number transcendental? So it was transcendence theory in number theory. And some of these proofs, like e to the pi or something, I mean, there are various things that are known to be transcendental. I forget what they are. Maybe it's actually like the square root of 2 to the square root of 2. The way they prove these is they look at estimates of some meromorphic functions or something, and in attempting to generalize these arguments to higher dimensional varieties, not just points in the complex plane, he needed to define some quantity that occurred as an exponent in one of these meromorphic functions. And that's where the Waldschmidt constant came from. He was trying to generalize some of this work. The Seshadri constant, which has gotten more attention, came later. Demailly in about 1991 or so invented Seshadri constants to study positivity in line bundles, basically. But they're closely related. So here's the relationship. Let me define f sub t of z. So f sub t of z will be a divisor. The t tells us the multiple of the class of a line, and the z tells us what the coefficients of the blow-ups of the points will be. So this is just convenient notation to indicate a divisor. But I can look at two divisors. I can look at the divisor where I have z as the negative part, and the degree of the divisor, so to speak, is the Waldschmidt constant. This is a limit of effective divisors. Because what I'm looking at here is a limit of the degrees where there's something in the ideal of m times z. So alpha of m times z is the least degree where I get something in the ideal of m times z. So this is the limiting degree asymptotically where there's a divisor that vanishes to the correct multiplicities at those points in that degree. Normalized by dividing by m, taking large multiples and dividing by m. But it's essentially essentially a divisor on the edge of the effective cone in the blow-up of the surface. So you can think of it as sort of a limit of pseudo-effective divisors. Now, the Seshadri constant, the way I defined it is the Seshadri constant is the exponent on the negative part. So I want to divide through by t. So I get a coefficient of 1 here, and 1 over t is now the degree of the divisor. So here I'm going to get f of 1 over e sub z. This is a limit of, well, this is a Neff divisor. Well, if you take the intersection of a Neff divisor with an effective divisor, it's non-negative. So what this tells me is the following. The intersection here is just going to be the Waldschmidt constant divided by the Seshadri constant minus the negative part is the same for both of these because I'm using the subscheme z in both cases. So what we get is the ratio of the Waldschmidt divided by the Seshadri constant is greater than or equal to the sum of the squares of the multiplicities. So the fundamental formula is the Waldschmidt constant is greater than or equal to the Seshadri constant times the sum of the multiplicities, the squares of the multiplicities. To save time, I won't go through the argument. I'll leave it as an exercise. But if the points P1 through PS are generic, if the points are generic and if the multiplicities are all equal, then the Waldschmidt constant is equal to the Seshadri constant times m squared s. They're s terms, but they're all equal. In particular, if we make it equal to 1, then the Boltzmann constant is equal to s times the Seshadri constant. The Nagata conjecture in terms of these quantities is the following then. The Nagata conjecture, we can write it either, there's a direct connection between the Waldschmidt and the Seshadri constant now. And so I can write the conjecture, well, let me write it all three ways. So we have C is effective and linearly equivalent to D times the class of a line minus the sum of the multiplicities squared, where P1 through PS are generic and S is greater than or equal to 9. So the first statement was that D is greater than or equal to the sum of the multiplicities divided by the square root of S. Now, in terms of the Seshadri constant, it turns out that the Nagata conjecture is equivalent to saying that epsilon of z is equal to, let's see, I guess I want 1 over the square root of s. Let's see, let me make sure that's right. Yes, that's what I want. 1 over the square root of s. And then in terms of the Waldschmidt constant, oh, what is z? Where the subscheme is just the union of the points. And in terms of the Waldschmidt constant, it is saying that the Waldschmidt constant is the square root of s, again for z to be the sum of the points. And this should satisfy this condition. So this, I'm saying, is the square root of s. This is 1 over the square root of s, and this is s. So this condition is satisfied. So where this is coming from is the following. The Nagata conjecture is coming from the fact that a Neff divisor always has non-negative self-intersection. And so therefore, the self-intersection of this divisor, this is the Neff divisor corresponding to the Seshadri constant. This has to be greater than or equal to 0. But what this is 1 over epsilon squared minus the sum of the multiplicities squared. So that has to be greater than or equal to 0. Now, in the case of the Nagata conjecture, what we have is the multiplicities are all equal to 1. They're s points of multiplicity 1. So this is 1 over the Seshadri constant squared minus s is greater than or equal to 0. And if we rewrite this, we have 1 over the Seshadri constant squared is greater than or equal to s, or 1 over the square root of s is greater than or equal to the Seshadri constant. So the Nagata conjecture is saying that the Seshadri constant is as big as possible. What that means is, in order for the Seshadri constant to be big, that means that the Seshadri constant is determined by the curves that it meets. By the Hodge index theorem, if the well, I'll get to that in a moment, but the value of the Seshadri constant gets bigger the fewer curves there are that can keep it, that are obstructions to being Neff. So if there's a curve that meets this thing negatively, then that means that 1 over epsilon isn't, it's too big. So being maximal, this is called if the self-intersection of this divisor is equal to 0, what that's saying is that epsilon is as big as it can possibly be. Because the bigger epsilon is, the more negative this intersection is. Getting the intersection down to 0 means that epsilon is as big as it could possibly be. And so we say in that situation that epsilon is maximal. The Nagata conjecture is thus saying that epsilon is, the Seshadri constant is maximal. If the Seshadri constant is not maximal, if it's less than what's required to make this equal to 0, in other words, if this divisor is positive, when the divisor has positive self-intersection, that's saying that the Seshadri constant is submaximal. It's not as big as it possibly could be, according to this fact that Neff divisors have to have self-intersection bigger than or equal to 0. So what that means is there are curves which, curve C, which prevent epsilon of Z from being maximal. In other words, the maximal case is when 1 over epsilon squared is equal to the sum of the multiplicity squared. So if I take the maximal value, that would be one over epsilon squared is equal to the sum of the multiplicity squared, and then I have to take a square root. This is not Neff. If this were Neff, then the Seshadri constant would be maximal. So this is not Neff. That means there's a curve that meets it negatively. And so that curve is the obstruction to having the Seshadri constant be maximal. But there are probably a lot of curves. And so what I'd like to do is I'd like to pick an extremal example of a curve that keeps this thing from being, that keeps the Seshadri constant from being maximal. So in particular, if the Seshadri constant is submaximal, then the self-intersection is positive, and I can find rational numbers. So let's say there is a rational, I'll call it lambda 1. Let's say lambda 1 is d1 over n1. Such that lambda 1 is less than 1 over epsilon. This is the degree of the divisor. So making the degree less reduces the self-intersection. I want to reduce the self-intersection but keep it positive. But because it's less than the 1 over the Seshadri constant, this divisor is not Neff anymore. So there is a curve C1 such that f of lambda 1 of z dot C1 is negative. This is effective, an effective divisor. Lambda is less than the Seshadri, 1 over the Seshadri constant, so this is not Neff, so there's a curve that meets it negatively. This is a rational number, so that means if I multiply this by n1, this will become an integral divisor. All of the coefficients will be integral. So n1 of f lambda 1 of z is an actual divisor. It's not just defined over the rationals. And you notice that if I want, this won't surprise this audience, but rationals aren't uniquely defined. So I can multiply the numerator and denominator by r, and that, when I do that, I'm taking larger multiples of this. Pardon me? Oh, lambda 1 is a number less than 1 over epsilon that keeps the self-intersection positive. But because the self-intersection is positive, if I take a large enough multiple of this, it will become effective. So this is an effective divisor. Well, rather than putting the r in, let me just assume that I picked d1 large enough that this is effective. So I can assume that this is effective. And so C1, or C1 is a fixed component of the linear system n1 times this divisor. All right, what I want to do now is I want to take a limit. I want to take a sequence of rationals. So now take a sequence with limit 1 over epsilon. And what I want is I want n1 to divide each of these additional n's. So I'll show you why I'm doing this. So what I'm getting now is all of these lambdas have these same properties. If I multiply the denominator, this thing n2, ni f lambda I z is an actual integral divisor. It turns out this is effective. I'll show you why in just a second. But there is a curve C sub I, which meets it negatively. And that's because the lambdas are all less than 1 over the Seshadri constant. Now the reason it's effective is let's see, what is the formula I wanted? You can check, it's relatively easy. N sub I times f lambda sub I of z. Here I'm using the fact that n1 divides all of these. This is equal to ni divided by n1 times n1 f lambda 1 of z. The n1 divides the ni, and so this was effective. I'm just multiplying by an integer, so the result is effective and integral. But the difference is that the degree is coming from the numerator, and I have to add something because these fractions are getting bigger. And so what I add is ni lambda I minus lambda 1 times L. The lambdas are getting bigger, so this is also effective. So what this means is this divisor is actually a multiple of the original divisor plus a multiple of the class of a line. So the fixed components of this divisor are a subset of the fixed components that I started with. And so that means that Ci is a fixed component it's still a fixed component of the same divisor that I started with. It's actually a fixed component of this, but because I'm adding on this positive part, some of this fixed locus will disappear, but in any case, it gets smaller. It can't get bigger. So all of these curves are fixed components. They're only finitely many curves. And so that means one of them occurs infinitely often. So therefore, some fixed C has the property that f lambda I z dot C is negative for infinitely many I. But now I can take the limit as I goes to infinity of this. Well, let me take the limit only of the subsequence. Well, the limit of this thing is equal to the limit of the f sub ij well, when I take the limit, I don't know that it's still negative. It might be 0 in the limit. So I have to change those to inequalities. But this thing here is f of the limit of the lambdas is 1 over epsilon. The limit is less than or equal to 0, but this is nef and this is effective, so this is greater than or equal to 0. So that means there is a curve which is orthogonal to this. So there exists a reduced. So the theorem is if the Seshadri constant is submaximal, which means that 1 over epsilon squared is positive, then there exists a reduce irreducible C such that the Seshadri, the curve dotted with the divisor here is 0. Such a curve C is called a Seshadri curve. It's not necessarily unique. Sometimes it's unique. It doesn't have to be unique. But you can see there are only, there are only finitely many possible Seshadri curves. It turns out they're all going to be fixed components of one of these divisors. What's also interesting and what makes it relevant to this series of lectures is that it has negative self-intersection. It's got negative self-intersection because this is a curve of positive self-intersection. And this is orthogonal to it. So by the Hodge index theorem, this has to have negative self-intersection. So Seshadri curves are examples of negative curves. And in fact, you can use this to try to compute the Seshadri constant. Here is a result that allows us to compute the Waldschmidt constant. So here, let me state that result. So the theorem is if F is a Neff divisor, so let P1 through PS be points of P2, not necessarily generic, just points of P2. And Z is some fat point subscheme. If F is a Neff divisor, and if you can find some divisor of this form which is effective, such that F, the intersection of the Neff divisor with this divisor is 0. Then the Waldschmidt constant is D divided by R. And a similar result holds for epsilon. For the epsilon, for the Waldschmidt constant, I needed the effective divisor to be in a nice form, and I just needed a Neff divisor. For the Seshadri constant, we need an effective divisor, but the Neff divisor will have to be in this form, and you'll get the same result. And the proof is easy, actually. The fact that this is 0 essentially means that this ratio is as small as it could possibly be, and therefore it's the Waldschmidt constant. Well, I had a little more to say, but I think this is enough since we're at the end of the hour. So I'll stop here.